So we have, again, an ambitious agenda for what I'm hoping for us to get through today. And it all starts with the topic that we didn't quite get to a week ago, which is the topic of subspaces. So we sort of just waved our hands at them a little bit and said, well, a vector subspace is just a vector space that lives within a larger vector space. And that's not untrue. But in their own right, subspaces can be an interesting thing for us to look at. And so I think it deserves a little bit more attention than we gave it a week ago. So let's just do one activity inside of the subspaces section that can help us to kind of get an initial grasp about what subspaces are, where they come from, and how we can understand them. Because one of the main goals for us today is going to be to discover how I can describe an entire vector space, whether that's a big space or a smaller subspace within it, how I can describe that whole infinite collection of vectors just by specifying some small finite list of vectors that we're going to call a basis. So it's called a basis for a subspace or for a vector space because it's sort of the foundation on which the whole rest of the vector space gets constructed or built. If you tell me a basis for a vector space, you are giving me enough information to reconstruct the entire infinite set, which is that vector space. All I have to do is take the set of all linear combinations of that basis, and I get the whole vector space back. And so if we know what linear combination and span mean, then we are 2/3 of the way to understanding what a basis is. And actually the third element we talked about last week, that's linear independence. So when we see what a basis is in a little while, a basis for a subspace is going to be the smallest set of vectors necessary to describe the entire space, but also the largest set of vectors which does so in an independent way, so that none is redundant with the others, so that none is a linear combination of the others. A basis for a vector subspace is a spanning set for that subspace, which is also linearly independent. So there's the definition of the day. Basis is linearly independent spanning set for a vector subspace. And as soon as you tell me a basis for a vector space, you have told me everything I need to know about that vector space. So we'll start with subspaces, and then we're going to back our way into a discussion about what is a basis, how can I tell when something is a basis for a vector space, and then how can I discover a basis for a given vector space, so that it's almost like a pocket-sized version of that vector space. We can take just 2 or 3 vectors, put them in our pocket, travel across the country, give those vectors to somebody else, and then they can reconstruct the entire vector space from just those 2 or 3. It sounds like a funny metaphor, but really it's not that different from, for example, what error-correcting codes do when you are sending information across long distances over telephone wires. That the way you can sort of cancel out the noise in that is through a similar type of process. Same thing with encryption and decryption, also kind of works on those same type of principles. So all of that is a large check that I'm not going to be able to cash completely today, but we'll get the basics of what we need to know for the introduction. So let's start with subspaces. As we talked about very briefly in our last class, a subspace of a vector space is just a vector space that lives inside of a vector space. This screen hasn't done a very good job of showing it to us, so I guess I'll do the illustration myself. But it says that the span of these 2 vectors forms a planar subspace inside a larger vector space R3, and I think that the diagram that they had in mind looks something like this. So here's my 3-dimensional vector space R3. And inside of that 3-dimensional vector space, maybe we place 2 vectors. Let me call them V and W. So there's a vector V. And then here's a vector W. And let's make it so that V and W are not parallel to one another. In other words, they are linearly independent. They form a linearly independent set. So here's my V and my W. And if I take the space of all linear combinations of V and W, it's going to form for me a plane. And I call that plane the span of V and W. We learned that word a couple of weeks ago. So I'm going to call this capital W. It's the span of the 2 vectors. But we also would call this a subspace of my 3-dimensional space, R3. Right? So it's a subspace of 3-dimensional space because we can show that it forms a vector space in and of itself, right? And also, it happens to reside within the larger vector space, R3. I mean, there's not really much more to the definition of what a subspace is than that. It is a subset of a vector space, which, using the same addition and scalar multiplication operations as the bigger space, forms a vector space in and of its own right. So if that's the definition, then what can we do with that kind of thing? So how are we going to think of this as being interesting? Well, here's a pretty important set of facts that we can use to determine when something is a subspace. As you might imagine, if we already have a bigger vector space, like in this example, three-dimensional space, R3, that big space already satisfies all 12 of those axiomatic properties that we looked at, I think it was last week, that make the big space into a vector space. And so if I want to study a smaller object within that space, it's pretty likely that a lot about that smaller object is also going to satisfy those same axioms that the big space did. And that's the case. And so it turns out there's only a couple of things that we have to check in order to verify when a subset of a vector space is itself a vector space. There's only two things we need. We need the set to be closed under addition. So we need it to be true that any two vectors from inside of my subset, their sum will also remain inside of that subset. So in this example, any two vectors v and w that I choose, let's say these are my two, if I add those two vectors together, and remember when I add vectors we get a picture that looks something like this in Euclidean space. Here's the other side of my parallelogram, call that v plus w. That if v belongs to my subset and w belongs to my subset, then their sum will also belong to my subset. Another way to think about this is I can't add two elements of my subset and have the sum of them not belong to that subset. I can't leave the subset by virtue of just adding things which are in the subset. That's what closure under addition is supposed to tell us. So that's one thing we need. For all vectors v and w in my set, the sum also has to be an element of that set. And the second is closure under scalar multiplication. That if you give me any element of the set and also a scalar, so also just a plain old number, c, then the product c times x, so the scalar multiple, belongs to my set as well. So, I don't know, let's say I take the number c equals -1/2, or something like that. So I pick a real number, -1/2, I multiply I multiply v by that real number, and so here is c times v. And the statement here is that for any v that I could pick, and for any constant that I could pick c times v is also an element of my set. So I can't leave my set by just multiplying elements of my set by scalars. Right? If I do that, I'm always going to remain within my set. So these are the only two things that we actually need to check. If we already know that the ambient space is a vector space, then a subset of that larger vector space will be a vector subspace as long as it's closed under addition and closed under scalar multiplication. So those are the only two things that we need to check in order to guarantee that what we have is a vector subspace. So here's where I'm going to turn it over to your teams in just a moment. In this example, we have a set of points inside of three-dimensional space. And that's a set of points whose x, y, and z coordinates satisfy x plus 2y plus z is equal to 0. Those of you who took multivariable calculus with me this summer will recognize that as being an equation for a plane inside a three-dimensional space. And so the question is, how can we prove that this set actually is a vector subspace, a subspace of three-dimensional space? And so this problem kind of walks us through the three steps to show that it's closed under addition, that it's closed under scalar multiplication, and then to try and deduce, is this thing a subspace of three-dimensional space? Peter, question? On the previous slide, it actually mentions, and I didn't call attention to it, but it's a good idea to, that every subspace, every vector subspace must contain the zero vector in its larger space. And one of the ways to see that is that if my space is closed under scalar multiplication, let's say, then I can pick any vector in my space and pick the scalar 0 and do 0 times my vector, and I'll get the zero vector, and therefore if it's closed under scalar multiplication, that set has to contain the zero vector. Same thing with closure under addition. I could just pick v and the opposite of v and add them together to prove that the zero vector needs to belong to a subspace. So the zero vector belonging is a necessary condition for a subset to be a subspace. It's not a sufficient condition, but like any necessary condition, what it can do for us is it can rule out examples that are not subspaces. And so the contrapositive of this statement here is that if I have a set that does not contain the 0 vector, then there is no way for that set to be a subspace, vector subspace of the larger vector space. So having 0 is necessary. Not having 0 rules us out for being a subspace. So let's take about 15 minutes. This is going to feel like a little bit of a proofy exercise, which is why I wanted to lead off with it today. And when you do this work, you should feel free to kind of, have a cocktail napkin version of what we're working on today and to kind of be satisfied with that just for the purposes of what we're doing. But if you do end up with a little bit of extra time, I certainly would not tell you not to try and write it up as something a little bit more polished in that sort of a 5-beat proof format that we've been working on. But for now, let's work on parts A, B, and C of this activity 2.4.1. They're in your team folders. And I saw that Luisa just arrived, and I'm going to ask Luisa to be the recorder for group 1 today. Luisa, we're doing a little bit different thing with our groups today. All right, so actually that went pretty well so far. So the idea was that we wanted to prove that if we have the set of vectors that satisfies x plus 2y plus z equals 0 in 3 space, that set is in fact a vector subspace of 3-dimensional space. And so this is group 3's write-up of what you did. And so what you've done here is picked a vector v and a vector w that belong to the set S. So what do we know about them? We only know one thing. We know that their x-coordinate added to twice their y-coordinate added to the z-coordinate is equal to 0. So that means that if v is equal to xyz, then x plus 2y plus z is 0. And if w is equal to abc, then a plus 2b plus c is equal to 0. So then the question is, if I add v and w together, am I guaranteed that their sum also belongs to the set S? And the only thing we know about the set S is that its criteria for membership is that the x-coordinate plus twice the y-coordinate plus the z-coordinate of any of its points is equal to 0. So we just have to check to see whether the x-coordinate of the sum added to twice the y-coordinate of the sum added to the z-coordinate of the sum is equal to 0. And that's the work that this team has done here. So if you take v plus w and you add its x-coordinate to twice its y-coordinate to its z-coordinate, you use the fact along the way that we know that the x, y, z are the coordinates of v and they satisfy this first equation, and that the a, b, and c are the coordinates of w, they satisfy that second equation, and the fact that they satisfy those equations is sufficient to guarantee that v plus w also satisfies this equation. So this is, again, what I sometimes call a cocktail napkin version of the proof, because it has all of the correct sort of steps of logic that we would need in order to craft a proof out of this. It's just that some of them might not be in the right order, and we might need to add some additional words and some sentences to help a reader who's looking at this for the first time to understand what's going on in this proof. So, as always, I think it will be a good exercise for us to fill in the in-betweens. So, on this activity, the first thing in a formal write-up of this proof would probably be to, again, introduce the thesis. So what is it that we're about to prove? We're about to prove that the set S, that it consists of vectors in 3 space whose x-coordinate added to twice the y-coordinate added to the z-coordinate is equal to 0 is a subspace of R3. Second step is to set the context. And setting the context means that we should tell the reader, sort of create some new instances of variables. I'm thinking like a computer programmer here. Give me a meaning for a vector w and a meaning for a vector v and a meaning for a real number c. And then we're going to use those to do some reasoning. Actually, I'm going to change notation just a little bit, because I think that one of the places where it's really easy to get turned around when you use definitions is that the x, the y, and the z that are a part of the definition of our set up here, those are just placeholders. We could have called them anything we want to, right? I could have called this I, j, and k, such that I plus 2j plus k is equal to 0. And I'd be describing the same set in the process. And so there's a potential confusion that arises when our concrete instances of a variable as part of our proof, like this x, y, and z right there, use the same symbols as the general definition of something that came from the thesis statement. So I just think that that's a little bit confusing. So I'm just going to call the coefficients of my x, or my vector v, I'm going to call them d, e, and f instead of x, y, and z, just to avoid us getting twisted around. So when I set the context, I'm going to create a vector v and a vector w. they have components called D, E, F, and A, B, C. And I'm going to tell the reader these are both elements of S, so they belong to this set that we're interested in. And we're also going to pick an arbitrary real number, call it C. Then we're ready to state the hypothesis and the burden of proof. So we're going to show, this is the burden of proof, that the sum V plus W is an element of S, and that will prove that S is closed under addition. And then we'll also show that C times V is an element of S, and that proves that S will be closed under scalar multiplication. So all of this stuff ends up in our final written proof, even though it's stuff that when we're just working on a cocktail napkin, that's just kind of up in our head. It's often stuff that we're taking for granted. Yeah, so we have another notational collision. So we have a C that's a part of our coordinate of W, and we also have a C that is our scalar for this. So let's not use C. Thank you for correcting that. So these little notational crises are potentially very confusing to somebody reading this who wasn't us. Because even if we can keep straight in our mind while we're writing the proof that those two C's mean different things, there is no guarantee that whoever looks at this next is going to not be confused by that. So yes, the same letter should not be used to represent different things. Let's put it that way. Okay, so with that rescue having been made, let's turn the cocktail napkin work from over here into a list and warrant for our implications. So what's our burden of proof? We want to prove that V plus W is an element of the set S. And to prove that, we need to prove that its x-coordinate plus twice its y-coordinate plus its z-coordinate is equal to 0. So I'm actually going to say that as part of my burden of proof statement, just to be as explicit as possible about this. So to prove that V plus W belongs to the set S, we will show that its coordinates satisfy the equation x plus 2y plus z is equal to 0. So that is what it means to belong to S, that the coordinates of a vector satisfy that equation. So to do that, we need to know what are the coordinates of the vector v plus w. This is a piece that was sort of missing on the cocktail napkin. And so the first time I looked at the cocktail napkin that this group wrote, I was a little bit disoriented that this wasn't there, but it was clear from the context what they were doing. But for the sake of the reader, the coordinates of v plus w, remember, we've been playing around a little bit with defining addition and scalar multiplication in potentially very different ways. So we should probably show for the reader that addition means what they think it means. The coordinates of v plus w are, and then I'll just write them out. So the coordinates of v and w are d, e, f, and a, b, c. So when I add them together, I get d plus a, and e plus b, and f plus c. So we need to show that the x-coordinate, which is d plus a, plus twice the y-coordinate, which is e plus b, plus the z-coordinate, which is f plus c, is equal to 0. So that's the thing that I need to prove is actually true. And if you notice in the write-up on the cocktail napkin, that statement almost ended up kind of towards the bottom of the proof, but when we rewrite it, it ends up near the top. This is actually pretty common in how the translation from the sort of napkin version of a proof into a formal write-up works. In particular, it seems like when you take a course in a subject like real analysis, which is our Math 401, almost every proof that we write in analysis, by the time we finished it on a napkin, we end up rewriting it pretty much backwards compared to the way that we originally discovered it on the napkin in the final proof. All right, so how are we going to show that this is true? We'll do the usual thing that we do when we're trying to prove that an equation is satisfied. We'll take the left-hand side expression and we'll try to work it so that it equals the right-hand side expression without having to work on both sides at the same time. So d plus a plus twice e plus b plus f plus c. And so I want to show that this is equal to 0, but I don't really know anything about it yet. What I want to do, going back to my cocktail napkin for some inspiration, is I want to try and do some algebra that I know I can do, so algebra of ordinary numbers, right, that can let me maybe get rid of these parentheses, right, which is what we would do if we were going literally backwards on this step. So I could take the parentheses away from the x plus a and the z plus c, and I can distribute the two across the addition in y plus b, or in my case, e plus b. So this would then be equal to d plus a plus 2e plus b plus f plus c. And then the warrant for that would just be by the distributive property of multiplication over division, or over addition. Just zoom in so you can kind of see the warrant here. If this gets too small to read, please let me know. All right, so there's the first step. We've got our parentheses gone. Now we need to do some rearrangement of terms. It would be wonderful to get the D's, E's, and F's close together so that we can say something about them, and likewise with the A's, B's, and C's. And this, again, is the next step backwards on the cocktail napkin version, right? All the X's, Y's, and Z's are close together, and then all the A's, B's, and C's are close together.
Professor, I think you lost a 2.
I think
I did. It's supposed to be 2e plus 2b.
Yeah, it's been a long day for me. Sorry about that. It has been a long day for me. There we go. Cool. Thank you. Thank you for keeping me honest. I know that I have some faculty colleagues who will give their students like prizes for catching mistakes. I would never do that because I would run out of prizes like on the first day of class. But yes, no, that 2 is real important. We would not be able to get where we're going without it. Okie doke. So with our 2 back in place, then what we would need to do is, get the D's, E's, and F's close together. So D plus 2E plus F. And then the A's, B's, and C's, A plus 2B plus C. On the right-hand side of my equal sign. And so that is, again, if we want a warrant on this, and we probably should have one, by the commutative property of addition. Right? Addition doesn't care which order we add in, addition of real numbers. In fact, it's one of those properties that is essential in defining a vector space, is the commutativity of the addition operation. Okay, and now that we have those things together, now is the time for us to use what we know about the numbers A, B, C, D, E, F. And what is it that we know about those numbers? We know that D, E, and F together satisfy something. And we know that A, B, and C together satisfy something. And I can group those things together, and I'm being really pedantic now, by the associative property of addition. I can just put those parentheses in there, right? Now, at some point, did we say, I guess we didn't. So we didn't say up here, but you did say in the cocktail napkin, so this was something you wrote down and I probably should have, that the ABC and the DEF satisfy these equations, which tell us essentially that those vectors belong to the set S. So we should make that assertion somewhere up front. We could either make it here or we could make it as part of our implications. And depending on your audience, one of those might be more appropriate than the other. Maybe now would be a good time to just make it as a part of the warrant for the next statement that we're about to make. So D plus 2E plus F is equal to 0. So I'm going to do this kind of in 2 steps, just to be able to write 2 different warrants here. So the first warrant is that since V belongs to S. So since V belongs to S by assumption, that means that its coordinates, D, E, and F, satisfy D plus 2E plus F is equal to 0. And so I can replace D plus 2E plus F by 0 as part of that proof. And then on the next step, I would replace the other, A plus 2B plus C, with a 0. And then that happens since V, or W rather, belongs to S. And then of course 0 plus 0 is equal to 0. And I don't think we need a warrant for that one. So when we look at this whole thing from beginning to end, so far, what we have, right, is I added V plus W together. And then I figured out whether its coordinates, its components, satisfy the equation that it's supposed to satisfy in order to belong to S. Right? And so that was my burden of proof. I needed to show that D plus A plus twice E plus B plus F plus C equaled 0. And then I did the calculation with a warrant for every step and found out that yes, that was indeed the case. And so, fortunately, that brings us to the end of this portion of the proof. Therefore, V plus W So this is kind of a sub-restatement of conclusion. V plus W belongs to S as asserted. And S is closed under addition. Sometimes at an intermediate step at the end of in the middle of a proof when we're not quite done, rather than using our full end of proof little symbol, we'll use like a diamond or something, just to kind of say, all right, I've established one of the subclaims that I set out to make. And then once we get to the very end, therefore, we have shown that S is vector subspace. That's where we put the big black square for end of proof. Right? So sometimes I'll just put this little intermediate step in there. Okay. Same story for the scalar multiplication. I'm going to abbreviate this one a little bit more. Same idea on the cocktail napkin as before, that if I have a vector that satisfies x plus 2y plus z equals 0, that relationship is still satisfied by a scalar multiple of it. The only thing I would do to modify what's on the cocktail napkin is I'm just going to change where the parentheses are placed, just a tiny little bit. So here to show closure under scalar multiplication, we need the coordinates of k times v. So I'll put those in. So those are kd, ke, kf. To show that this belongs to S, we need to prove that kd plus twice ke plus kf is equal to 0. So there's the thing that we need to prove in order to show closure under scalar multiplication. And so then that's what we'll do. So kd plus 2ke, and I'm typing in front of a crowd, which is always a fun time. So I need to know something about that statement. So what I want to do is try to take away the parentheses. Or maybe better yet, yeah, let's take away the parentheses. Why not? kd plus 2ke plus kf. We don't really need a warrant to do this, but I'm being especially fussy today by the associative property of multiplication. So my parentheses are gone. And now, what's my step? What is the actual step that's going to get me the closest to the finish line in what I'm doing? Keeping in mind that kind of what I'm doing is writing the cocktail napkin steps here in a backwards order. So let's factor out that k. If I factor out that k, it's going to make it so that that k, which I don't really know much about on its own, I know something about everything else, that we're going to get that k isolated by itself. And then what's going to be left over is exactly what we want to draw an inference about, d plus 2e plus f. And so that factorization is just, again, sort of properties of regular, plain old real number algebra. I would call that the by the distributive property of multiplication over addition, just applied backwards. Right? That's what factoring is, more or less, is the opposite of distributing. But then, now is where we use the all-important remembrance that d plus 2e plus f is equal to 0. And we know that d plus 2e plus f is equal to 0. Here comes the warrant, since we knew that v belongs to S. Since v belongs to S, d plus 2e plus f is equal to 0. And then k times 0 is equal to 0, which doesn't really need a warrant. And so we've satisfied the second piece of what we hope to do. Therefore, kv is an element of S, as asserted, and S is closed under scalar multiplication. I'll put our little intermediate diamond in there to show that this assertion has then been established. And therefore, we have shown that S is a vector subspace. Right? Because all that's required in order to be a vector subspace is that our set is closed under addition and it's closed under scalar multiplication. In other words, that for any arbitrary selections of two vectors v and w and constant k, that v plus w belongs to S and that k times v belongs to S. And I suppose the only other thing I'll add here is, since we had to draw these conclusions about d plus 2e plus f equaling 0 and a plus 2b plus c equals 0, since those are so important to the proof, I would put those up front here in setting the context. So once we chose v and w to belong to S, I would say something like, in particular, we have a plus 2b plus c is equal to 0, and d plus 2e plus f is equal to 0. And so here is a full rendition. So this is what the proof would look like if you saw it in a textbook or something. And again, quite different than what the first draft looks like when you write down on a cocktail napkin. So again, my goal for you this semester is that you're able to get some additional practice in going from cocktail napkin to something that's a little closer to this. You might not get all the way here in your practice all the time, and especially if you take a course, let's say in the fall, where you have to write a proof on an exam or something. The proofs you write on exams tend not to look like this, unless maybe you're in graduate school or something like that. But getting that practice will make you more effective at understanding and communicating mathematics at the upper level.